Acids and bases have two different faces, two different personalities. And you gotta find out what they're all about if you want to learn chemistry.
So you might have a clue that this deals with some acids and bases. So I'm at the toy store and I come across these Velcro glove things with these spheres. And I kind of look at materials differently. And I say to myself, you know, I could use this to teach acids and bases. Because if you think of this as a proton, we have an acid here where it can give up the proton. It's held rather loosely or strongly, depending upon the strength of the acid. So I've got a nice class here of 4 students, and I'm going to teach you guys a little bit about acids and bases. And I'm sure you're going to get it just like my students get it. So this is the Lowry-Bronsted definition of acids and bases. And already kids are blown away because 2 days ago we covered the Ingenious definition of acids and bases, and now we're going to give them a second definition, and they barely know the first one, perhaps. And then Lowry-Bronsted, it's a definition with 2 names. One guy, Lowry, was an English chemist in the 20s, and Bronsted was a Danish chemist in the 20s. And they came up with the definition, the idea simultaneously. Even at the same time, they came up with this idea. And here's our acid, and here's our base. Now, right away, the kids are going, I don't see any hydroxide. That's a bad part, too. Their brain, already they're a little bit messed up. And then we say, well, it's not bad, kids, because an acid is simply a proton donor. And they're going, well, where did the proton come from? The nucleus of something? No, this is a proton that's really a hydrogen atom with an electron ripped off. So it's really this hydrogen atom with the electron removed, because the most common isotope of hydrogen is just got a single proton. So that's a little hard for them to swallow. Don't let them do that literally, but that concept is a little hard for them to it's not that palatable. So, but it's really not bad if you think of it, okay? Because you take the H and you donate it to this, which is acting as a base, and that's a proton acceptor in the Lowry-Bronsted definition. And so then you end up with HB, which kind of makes sense. This has accepted the proton, and A minus. And so they're going, yeah, I see. So it's really easy. You look at this, and the one that gives up the H is the proton donor. So that's the acid. And the one that accepts it is the base. They're going, great. And what are those other 2 words? Conjugate acid and base. Well, conjugate means they're paired up with something. So this is the acid, and this is its conjugate base. And it's really not hard. They just differ by an H. This is a base, and this is conjugate acid. And so they just differ by an H. So they're going, well, I guess I get that. I guess I kind of get that. These 2 are related then. And of course, it is an equilibrium, so they can go back. This can act as an acid and put the proton on here, and this can act as a base because it accepts it. So they sort of get it. Do you guys sort of get it? Yeah. So I'm going to give you an assignment. You're going to go home tonight. You're going to work on some problems, solve some of these, and come back tomorrow. All right? So then tomorrow they come back, and I say, you do the homework, any questions? And no, we got it. We looked up the stuff in the back of the book, wrote it on the paper, and then we're done. So I'm going to give you guys, each of you guys, a glove just like this, and you just have to put it on. And we're going to see if you understand the concept. And one of the concepts that you read about yesterday, too, was which one of these is the stronger acid, HA or HB? And the acid strength is how well it can donate a proton to the base. The stronger acid will be able to donate the proton the best. The stronger the acid, the weaker its conjugate base. And the weaker the acid, the stronger its conjugate base. So really, it's not too bad, is it, guys? No. Wait till we get to the Lewis acid-base theory. All right, so I'm going to drop this on the floor. And the strongest acids, there's only going to be 2 of you 4, will get extra credit. Kids will sell their grandmother for extra credit. All right? Or there could be a little prize, whatever you want to give out. So on the count of 3, remember now, the strongest acids are the winners, the other 2 are the losers. You're going to go for, these are protons now. You guys are the anions. Ready now? 1. Some of you are cheating. 2, 3. Okay. Now at this point, you ask the class, which ones are really the stronger acids? The stronger acid is the one that wants to give up the proton. So I'm going to lose this one and put up the other one, and don't go transferring it behind my back. All right? So in this case, the way this scenario plays out, and this is a diagram from John Fortman from Wright State, the stronger acid in this case is HA. It will take the proton, shove it down the throat of this base, forming this conjugate acid and this conjugate base. Going back, this is an equilibrium that's favored for this side because this is the stronger acid, this is the weaker acid. So in this case, the weak acids are the ones that really don't have the protons, or that have the protons, and the stronger acids are the ones that gave up the protons. So you guys are the winner. Flynn, I'm sure, will give you some big certificate, some big award. So that's the first one. And what this does is it gets the kids to rethink about what's going on. It's kind of an assessment. And by the way, everybody, it doesn't really matter how smart they are. They all go for the protons. It doesn't really matter. I've had a kid that was in the chemistry Olympiad. I mean, he was a huge kid. He just pushed everybody out of the way. He almost had 2 protons. He almost was a diprotic acid because he wanted to get that prize. All right, so you two guys are done, and you're actually lucky to be done because you two get to wear these wonderful hats now. Flynn actually carries these gloves. They don't carry these hats. These are a little bit more expensive, and as you can see, they're quite stylish. And I'm going to make you guys into a water molecule. Oops, there you go. So these are water molecules. And so in this case, we have water and water. Water is amphoteric, which means it can act as an acid or a base. So one of these waters is going to give up a proton. In this case, it's formed the OH. So you're very basic. Okay? And we're left with an acid here, the H3O plus. Okay? So we've had this reaction. So let's start again. Grab your proton. We'll start again at the beginning. And I'm going to be an arrow here. Okay. So now I want you to react. I want you to auto-ionize, not in public. All right, there you go. Now I want you to shift to the other side. Excellent. So now we form the conjugate acid and base. Now we're going to go back the other way. And you need to come back here. Now, at room temperature, because of the equilibrium constant, which you're all familiar with, this is the favored form of water. There's only a small amount of H3O plus and hydroxide ion. So this is another way to look at it, too, with perhaps a more unique and embarrassing way to do this sort of a demonstration.